Okay, in the last video we saw how moles can be used to compare things and how we have moles as a number of molecules or particles in substance rather than a mass or a volume. But there are linkages between those two. And we saw the fact that the RAM of an element has a big link to the mass of a mole. If it's a monatomic substance, of course, then the RAM in grams is the mass of 1 mole. If it's a diatomic substance like O2, oxygen, then it becomes double the RAM, because I've got 2 atoms per molecule. Double the RAM equals the mass of 1 mole in grams. But okay, so we've done that. Now, normally in chemistry we do a lot of equations. And we've got a simple little one here where we're burning hydrogen in presence of oxygen to make water vapour. And we can see that it's given us in terms of molecules and moles. So the number in front of the symbol or formula is going to talk to us about the number of moles. Now we always have those as whole integers. We don't leave them as halves and things like that. All they are is they are a ratio. So in other words, the moles of hydrogen to oxygen that I'm going to need is 2 moles of hydrogen for every 1 mole of oxygen. The equation tells me that. Now I know this is a simple equation, but the same idea permeates all through our chemistry, as we're going to find out in a moment. And as we go through, we can work ourselves from a simple thing to solve a complex problem by simply using some of our basic ideas. Chemistry, equations and balancing, and this is why it's so important to balance our equation, because we know that a balanced equation tells us that we have conserved the mass. And that is one of the laws of chemistry, and it is really, really important law of chemistry, and that's one we'll have to go through later on in a bit more detail. But that means the first thing you do is put the correct formulas down and then balance them so that the number of atoms as reactants and products are identical. So all we're doing in a chemical reaction, remember, is simply rearranging the atoms. We don't get rid of some, we don't add some extra ones. No, what we start off with and what we end up with in terms of atoms are identical. But by no means does the number of moles of substance have to be identical. Alright, so that's one thing we need to remember as we go through. The trick that seems to bring people undone, and the questions that seem to bring people undone in quantitative chemistry, are when we have more than one reaction occurring. So it could be a sequence of reactions where one thing is used to make something else. And we do a sequence of things and we are expected to link the number of moles. And it's quite easy. It's just the same principle as we saw in the initial equation we had, which was 2 hydrogens mixing with 1 oxygen to make 2 moles of water. Alright, so the same idea works all the way through. And all we do is we link the whole mole numbers. Even though we probably haven't used 1 whole mole, it doesn't matter. We can still see the ratio that exists between the chemicals in an equation. And that's what an equation shows us. Even though we just use whole numbers to make it easier on our math. Right, a typical question might start off something like this. One of the many mandatory labs we have to do in chemistry is look at the amount of oxygen that's dissolved in water. And they use what's called the Winkler method. And it's a oxidation and reduction, more about that later, equation that involves 3 separate steps. All right? But we're interested in, because what we do is we look at the last step. And the last step allows us to come up with the moles that will allow us to work backwards and work out how much oxygen we had initially. So I've given you what sounds like a really, really, really hard question. And I've talked about the fact that a student did this and it was a titration, and she found she only needed 7.6 cm cubes of 0.025 molar thiosulfate to reach an endpoint. And then it talks about a temperature and a volume of her sample size. Now the question is about how much oxygen we had to start off with. Looks really hard, so let's break it apart and make it a bit easier on ourselves. And all we're going to do is we're going to use what we have in front of us and a simple moles calculation. Whenever you get a moles question, always start with what you know. Now, in any solution, the number of moles is going to equal the concentration of the solution times the volume you have of it. Now, we had in our question a concentration and a volume. And so if we then are able to put those in, we see that we've got a concentration of 0.025 molar, or moles per decimetre cubed, and a volume of 7.6 cm cubed. But our molarity or concentration is measured in moles per dm cubed. So the only trick we have to do is remember to convert our volumes into dm cubed. So that would be 7.6 divided by 1,000, or 0.0076 dm cubed. So just a simple bit of calculation produces this. Now, I've used scientific notation for several reasons. It limits the amount of significant figures I have, and it also looks a bit neater than lots of zeros, because I could easily lose track of the zeros as I go through this thing. So it works out that we had 1.9 by 10 to the minus 4 moles of thiosulfate. Now that in itself doesn't mean much, but that would have been the first part of the question, because the question would have been divided into sections, and part A would have been calculate the moles of thiosulfate, probably for 1 mark. So that little calculation there is worth 1 mark in an exam. Now here comes the tricky part. All right? The tricky part would be the fact they've given me these equations. And I look at that and go, oh my goodness gracious me, what am I going to do with this? Well, it's quite easy. We look at the things we know and then work back. Now the thing we know is the thiosulfate. So let's put it in. So as you can see, I've moved the number of moles to sit above. It's not really 2, but it's 1.9 by 10 to the minus 4. And I've set it above the thiosulfate ion there because I know that is my concentration. Okay, well that's my number of moles. And so what I can do that is put that there because I know I've had the information and I've calculated it out. Now as we see from here, what we've got to try to do is we've got to try to find something else in reaction 3 that also appears in reaction 2. And we've got 2 options. We can have the I2 aqueous, or we can have the 2I minus aqueous. I'm going to use the I2 aqueous. All right. So if we've got 1.9 by 10 to the minus 4, let's move him back to there underneath. Whoops, there. Underneath, then I can see that the ratio between the I2 aqueous and the thiosulfate is 1 I2 for every 2 thiosulfates. So that means the number of moles of I2 will be 1/2 of the number of moles of the thiosulfate. So, okay, 1/2 of 1.9 by 10 to the minus 4 should equal, as far as I recall, 9.5 by 10 to the minus 5. So there's my moles of I2. Now you know what? The I2 mentioned in reaction 3 is the same I2 as that mentioned in reaction number 2. Alright, now this becomes quite convenient for us, because if we know that the value of this is 9.5 by 10 to the minus 5, then we can work out the number of moles of all the other chemicals on here. Now, the one we're interested in probably most particularly is something that is going to appear in the equation above. Now, in the equation above, the one that does appear is MnO2 solid. Okay, so if we look at the numbers in front of the I2 and the numbers in front of the MnO2, we see that the mole ratios are the same. In other words, if I've got 9.5 by 10 to the minus 5 moles of I2, then I've got 9.5 by 10 to the minus 5 moles of MnO2. Okay, so we've started off by knowing the number of moles of S2O3 2 minus, and we've worked out how many moles of MnO2 we had. Hey, this is getting cooler and cooler. Really, really easy. It's not too hard. Alright, things are starting to now look a lot clearer, because we worked out that we could use thiosulfate to work out how many moles of I2 aqueous we had. Then we could use I2 aqueous to work out how many moles of MnO2 we had, and we end up with the fact that MnO2 is 9.5 by 10 to the minus 5 moles. Hey, this is looking pretty good. Now, if we look then at over to oxygen, we see that the ratio between oxygen and MnO2, I don't care about the other chemicals, I only care about the oxygen, is 1 mole of oxygen for every 2 moles of MnO2. This means the moles of oxygen will be half the number of moles of MnO2, which means we've got 4.75 by 10 to the minus 5 moles of oxygen. Hey, we've started off with moles of S2O3, 2 minus, and gone all the way to work out how many moles of oxygen we would have. Now, the only thing is, we've made the assumption that there is 100% yield in all of these equations, and that all of the chemicals that are being used as reactants came from the products in the reaction before. And they're not too bad of assumptions to be making, so we can live with that. So that works out really, really well. So can you see now that if we use moles and equations, regardless of how many equations we've got linked together, we can actually see how much we need, or how much we make, or how much we started off with. Now, that's a typical IB question. So they would have asked you to deduce the number of moles of oxygen from the number of moles of S2O3. Do you think you'd be able to do it now? I hope the answer is yes.